welcome to the lesson 14 class activities. On the axes below, you're supposed to graph the square root of x by hand, and then also graph these 4 functions shown here, the 3 additional functions. So I already did that. I didn't do it by hand. I did it using GeoGebra just to save us a little bit of time. And we're going to describe these transformations in our own words here. Describe what happened to the original graph of f to get each of the new graphs. So let's look at f and g here. So my green graph and my red graph. So look at some corresponding points. So some points with the same x value. So I've got one here and here. So my y value goes from 1 to 2. So it might be helpful to list the points here. So I have 1, 1 goes to 1, 2. And then let's see, another good point would be this one and this one. So I have 4, 2 and 4, 4. 4, 2 goes to 4, 4. And then 9, 3 goes to 9, 6. So what it looks like is happening is my y coordinates are doubling when I'm looking at f and g. And the formula bears that out, right? So if my g of x is 2 times the square root of x, so I'm doubling the square root, which means my y coordinate is doubling. So to describe this, to get the graph of g from the graph of f, we would take the graph of f is stretched vertically times 2, or by a factor of 2. All right, now let's compare f with h. Erase what I have here. Okay, h is the blue graph. So f is green, h is blue. And it's negative the square root of x. So it looks like you're taking the square root and then making it negative. So I'm going to expect that my y coordinates are just going to be opposites. So I have 1, 1 and 1, negative 1. And then check the next nice y value. I have 4, 2 and 4, negative 2. And then I have 9, 3 and 9, negative 3. So my y coordinates are becoming opposites. And you can describe this graphically as a reflection over the x-axis. Okay, my x-axis is acting like a mirror and I'm reflecting over it. So I would describe the graph of h as the graph of f of x reflected over the x-axis. All right, and finally I got to do the graph of k. Erase everything I've got up here already. How does the graph of f relate to the graph of k? So k is my purple graph, and it is 0.5 times the square root of x. So if I compare y values that at the same x value, I have 1, 1 becomes 1 1/2. And then 4, 2 becomes 4, 1. And 9, 3 becomes 9, 1 1/2. So it looks like my y coordinates are halving, 2 to 1, 3 to 1 1/2. So that I'm going to describe geometrically or graphically as the graph of f is shrunk or compressed vertically because it's the y coordinate that's changing, so we describe that as vertical. by a factor of 1/2. The y coordinates are all being multiplied by a half. Okay, I recopied the formulas up here. I want to find all of my y values for an x value of 1. And we can see that, that the relationships that we predicted hold. So f of 1, plug a 1 into f, you get 1. G of 1 is 2. H of 1 is -1. And k of 1 is a half. So G, we said, is a vertical stretch by a factor of 2. 1 times 2 is 2. H is a reflection over the x-axis, and 1 and 1, -1 are reflections over the x-axis. And k is a vertical shrink by a factor of a half. 1 times a half is a half. We could do this again for 9 and see the relationships also hold. I'm going to skip that. I'm going to rewrite g, h, and k as a transformation of f. So g of x, I'm going to go back up and look at my formulas here. G of x is 2 times the square root of x, but the square root of x is the formula for f of x. So instead of 2 square root x, I could write 2 times f of x. And h of x is negative square root of x, but square root of x equals f of x, so I could write this as negative f of x. And k of x I could rewrite as 1/2 times f of x instead of square root x. And I'm going to apply the transformation to a few points on f, find the corresponding points on the function h. So h is the -1. That's a reflection over the x-axis. And we can find that out by multiplying the y coordinate by a factor of -1. Multiply the y coordinate by -1. That will take all your y's and make them the opposite sign. So some points on f. F was the square root of x, so I've got 0, 0, 1, 1, 4, 2, 9, 3, 16, 4. I'm going to take the opposite of all my y coordinates. You can get them by multiplying by -1. So I have 0, 0, 1, -1, 4, -2, 9, -3, and 16, -4. Okay, again, you're being asked to graph two functions by hand, square root x and square root of 2x. The 2 this time is under the square root as opposed to outside the square root, which it was in the last example. So I already did this using GeoGebra, tried to save us a little time. And I want to describe what's happening with the transformation. So whenever you're changing the x, you're comparing x values with the same y value now instead of y values with the same x value. So I'm going to look at some y values on f and compare its x value to the same y value of g. All right, so let's look at a y value of 4, right? So, sorry, that's an x value of 4. My y value of 2. So y value of 2. On f, the x value that gives 2 is 4, but on g, the x value that gives 2 is 2. So my f point is 4, 2, and my corresponding point on g is 2, 2. So those are the 2 points on f and g with the same y value. All right, let's look at 2 points on f and g, another 2 points with the same y value, maybe a y value of 9. Right, so I've got here on the green graph, and then here on my red graph, y value of 9. Oh, that's a 3, sorry. Yeah, that's what I want, y value of 9. Y value of 3, y value of 3, and a y value of 3. Okay, so my point on f is 9, 3. The point on g that also has a y value of 3 looks like, that's 5, so 4.5. And maybe we'll do one more. I'm going to do 16. So a y value of 16 on F, that happens at, sorry, a y value of 4. Y value of 4 happens at 16 comma 4. So 16 comma 4 on F. The corresponding point on G, a point on G that has the same y value, happens at an x value of 8, 8, 4. So it looks like what's happening is my x values are being cut in half. So I have 4, 2 to 2, 2, 9, 3 to 4.5, 3, and 16, 4 to 8, 4. So the y values are being cut in half in order to produce this. The x values are being cut in half in order to produce the same y value. So that's what I just did all this. Okay. In order to get the same output for f and g, the relationship between the value of x in g and f is that you have to have it. Have the x value from f. Okay. So this is causing a graphical shrink, right? We are shrinking because you have to take only half of the x value that you did before to get the same y value. So graphically, I can imagine that the way I got the graph, this red graph, is I took the green graph and I put my hands on the left and right hand side and squeezed in. And that made the graph of G. All right, I want to write g of x, which is the square root of 2x, as a transformation of f. So this has been changed prior to the square rooting. So this is pre-operation. So I'm changing what's inside the square root, what's inside the parentheses. So this is f of 2x. Change what's inside. So you put the times 2 on the inside. I want to apply the transformation to a few points on f, find the corresponding points on g. So some points on f would be 0, 0, 1, 1, 4, 2, because remember f of x is the square root of x, 9, 3, and 16, 4. All right, so g of x is f of 2x. And we just determined that to get the same y value, to keep your y value the same, you actually have to plug in an x value half as big as the one you did on f. So I'm going to take half of all my x values here. So half of 0 is still 0. And then this is going to be 1/2 comma 1, 2, 2, 4.5, 3, and 8, 4. All right, one more. Graph of two functions, square root x and the square root of negative 1/2 x. So everything that's being changed in the formula is under the square root. So both of these transformations are horizontal. The 1/2 means I'm actually going to stretch the graph horizontally, and the negative is going to be a reflection over the y-axis. So we can see that by doing a few points that have the same y value. So I want to pick, let's say, a y value of 2. So here's one on f, and here's one on g, right? So f is at 4, 2. And the point on g, oh, sorry, k, the point on k that has the same y value is negative 8. That's the x value that gives the same y value. And then let's do a y value of 9. Okay, so on f, the point is, sorry, it's a y value of 3. The point is 9, 3. And on k, the point that has a y value of 3 has an x value of negative 18. So I have negative 18 comma 3. So in order to get the same y value on k as you have on f, you have to double the x and make it negative. So 4 becomes -8, 9 becomes -18. Double the x and make it negative. So that's sort of the opposite of what you might expect from seeing a 0.5. We're actually doubling. And that's a theme that happens when you have transformations inside the function. Horizontal transformations are sort of the opposite of what you might expect. So you see a 0.5, you might think shrink, but what actually happens is you are doubling, so you're stretching horizontally. So I basically just did 16 and 17. So the graph is stretching horizontally. And the other change to the graph is a reflection over the y-axis. I want to rewrite k of x as a transformation of f. So I just have to change what was under the square root. What was under the square root changed, so I have to change what's in the parentheses of f, -1/2 x. I'm going to apply the transformation to a few points. I actually did this for 2 points already, but I'm going to write it out. So I have 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. Those are points on the square root of x. And the -1/2 x, that's a transformation where I'm changing the x value. So it's going to sort of do the opposite of what you think. So I'm going to multiply all my x coordinates by a factor of -2. All my x coordinates by -2. So 0, 0 stays where it is, and 1 times -2 is -2. Then -8, 2, -18, 3, and -32, 4. So to summarize, stretches, shrinks, and reflections. If f of x is our basic graph, also known as a parent function, c is a positive real number, then if you multiply f of x by c outside the parentheses, this is a vertical stretch or shrink, right? It stretches or shrinks f of x vertically because it's outside of the parentheses. If c is bigger than 1, you're multiplying by a number bigger than 1, then that's going to stretch. F of x stretches by multiplying each of its y coordinates by a factor of c. If c is between 0 and 1, so you're multiplying the y coordinate by a fraction, then this is a shrink. F of x shrinks, and you calculate the shrink by multiplying each of its y coordinates by a factor of c. It just happens that c is a small number, so it causes a shrink. If c is negative, then the graph of f of x reflects over the x-axis. Okay, the rules are different when you're multiplying the x by c. So that c now is in parentheses. And this is always sort of the opposite of what you think is going to happen. So c is a positive real number. So this is stretches or shrinks horizontally. Anytime you're changing the x coordinate inside the parentheses, you're changing horizontally. Multiplication means a stretch or a shrink. If c is a big number, you're multiplying x by a number bigger than 1, then this is a shrink, right? It's the opposite of what you think. Okay, dividing each of its x coordinates by c, or multiplying each of its x coordinates by the reciprocal, 1 over c. If c is a small number, it's a fraction between 0 and 1, then f of x stretches horizontally. And you calculate the size of the stretch by dividing each of its x coordinates by c, or multiplying each of its x coordinates by the reciprocal, 1 over c. If c is negative, then the graph of f of x reflects over the y-axis.